So good morning, everyone. I am practicing. I welcome you all on behalf of IEEE-IISc Women in Science and Engineering Group and IEEE Women in Engineering Bangalore section. So we are a group of around 20 members in WISE, and we organize lots of talks and events for to create awareness regarding what are the research activities happening in both science and engineering, and to encourage people, especially women, to join and pursue career in research, and also highlight the impact of women which women are creating in the STEM fields. So without any further ado, I would like to introduce today's speaker. So unfortunately, because of some unavoidable circumstances, our main speaker, Dr. Abra Roy Chaudhary, will not be able to deliver the talk today, but instead his PhD student, Mr. Mukund Mitra, is going to present. So I'll just give a brief introduction about him. So Mukund Mitra, he's a PhD student working at a robotics innovation lab under the guidance of Professor Abra Roy, and he is a robot enthusiast currently working on motion planning and navigation of mobile robots in Industry 4.0. He has been actively involved in making new creative robotics products dealing with their modeling, control, design, and analysis. So with this, I request Mr. Mukund to begin the talk. Thank you.
Yeah. Good morning, Prachi. Good morning, everyone. Am I audible?
Yes.
So let me share my screen. Is my screen visible?
Yes, Mukund.
Yeah. So the topic of our presentation today is human-aware robot motion planning using RRT algorithm in Industry 4.0 environment. So this paper has been published in Intelligence and Safety of Robotics 2021. It's a conference paper, and this work has been funded by Samaj Udyog project of Department of Heavy Industries under Government of India. So let me begin with this. So the contents of the presentation is first we will give a brief description of the motivation that why we are doing this, human-aware motion planning. Then we will go to introduction. We'll discuss some common terminologies regarding the topic. Then we will go to problem formulation, where we will discuss that how do we form the how we sequentially form the problem, and then we'll go to different methods that how we solve those problems, and then we will go to results that we have obtained using experiments and finally and verification with the real-time model, and then finally we will conclude this presentation by some conclusion and discussions. So uh, as we know that this is a industry 4.0. In industry 4.0 is different from the previous one, is that in industry 4.0 we employ robots. Earlier, apart from sensors and all those things, in industry 4.0 we talk about robots. So when we talk about robots, the thing collaboration is very much important. So as we can see that if we employ robots in industrial environment, there are some we need to be concerned very much about the safety. So as you can see from the as you could see from these videos that if the any human comes inside the workspace of the robot, then there could be a collision chance of both. So the thing is, we need to plan our robots and their workspace in such a way that it's out of the range of humans. So means there is a very big misconception is that if we employ robots in industries, so there will be a decrease in employability of humans and all such things. But the thing is just the opposite of it, because robots work in collaboration with humans. It's not like that they replace human beings directly from the industry. So because so we employ robots to decrease the cycle time, to increase the productivity and all those things. So when robots are there in the industry, it must means we humans who are working over there must feel safe in the environment. So we need some algorithms and all those things to drive one robot from one place to another. So in this video, it's a stationary manipulator, but there are many robots which move all around the industrial workspace. So coming to the introduction part. So for moving robot from the start point to the end point, we need some real algorithm which traces the robot from one point to another point. So in this paper, we have used rapidly exploring random trees or so-called RRT algorithm in a human-centric environment. So as you can see from this video 3, I will just show. So as the name suggests, so here in this video, you can see the yellow point is the start point and the pink point is the goal point. So our robot has to move from that yellow point to the goal point, and the red one are shown over here are the obstacles. Uh, yeah. So red one is seen over here are the obstacles, and this number is shown above are the number of iterations. So as we can see from the figure that this all these blue and all these blue lines they just signify means the trees of the branches of trees. So hence the name is rapidly exploring random trees. So so in this, the red are the obstacles, which can be any sort of obstacle, like in which are there in a workspace or an industrial workspace, like human beings or any other machines or some prevented area like this. So past research says that obstacle avoidance in mobile robots and manipulators is very crucial when we consider Industry 4.0 because the robots need to work in collaboration with humans. Then to make this possible, we need a suitable algorithm which geometrically determines the pose and position and orientation of different obstacles. So now we have two possibilities. First is that either we model the obstacles or we model our robot accordingly. So the thing is that obstacles are of various types. Means it has no foundations. We have no foundations on the modeling of obstacles. Means we have mobile obstacles like human beings. We have stationary obstacles like fixed base manipulators and all those things. So instead of modeling the obstacle, we prefer to model a robot instead. So uh, so we now model our robot and we just represent obstacles as bounding boxes for collision avoidance algorithm. So we have various methods like we have various control methods like artificial potential field method, Berg algorithm, A star, modified A star, which are widely used algorithms for motion planning. So potential field method, as you could see from here, that potential field method, as the name suggests, is that it assigns suppose you take it assigns positive charge to the robot and positive charge to the obstacle, so that robot and obstacle positive charges repel each other, so robot will never come in touch in the vicinity of the obstacle. And we assign negative charge to the goal, so that robot directly which is positively charged has a natural affinity to go towards the goal. So it uses this method. This bug algorithm, it has nothing to do with or that bug that we are thinking. Basically, this bug algorithm uses a straight line method, and means it draws a straight line from the robot to the goal, and whenever an obstacle comes in between, it just traces the path of the obstacle around 40%, and then it again moves towards that straight line. So it's the bug algorithm. Similarly, we have A-star algorithm, which is more based on heuristical methods. Means we assign we model the obstacle here as nodes, and we assign every nodes a particular value, and then through back propagation we find the minimum cost to go from the start point to the goal point. So this is the A-star algorithm. There are many such algorithms for path planning, but as mentioned, they are very much computationally expensive. So in such situations, RRT means rapidly exploring random trees, proves to be the best option, means more efficient option than these other algorithms for generating open loop trajectories, specifically for nonlinear systems and obstacle avoidance, and in complex cluttered environments in industry. So RRT star integrates RRT with near neighbor search to generate optimal path with minimum path cost. So RRT star is nothing but a slight modification in RRT original RRT algorithm. See, RRT it rapidly explores its search directions in random areas. So RRT star instead of using that random word random fashion, it has defined itself a particular radius, and it searched the nearest neighbor in that particular radius only. So it's a bit less computationally expensive than RRT algorithm, but nevertheless both have almost same efficiency. And we test out this RRT algorithm in various distribution of obstacles. Like obstacles have various weight distributions. Like we model basically in this experiment in this paper we have modeled the obstacles as 12 types of obstacles which is commonly found in industry. I will talk to it later. So in our first we have first we have simulated the thing in MATLAB and Python, and then we have validated our simulation results. Not validated, validated and both experimented our simulated results in our Smart Factor Lab in CPDM department of IISc. So in simulation of MATLAB, but first we use inverse kinematic method. So when we talk about stationary, so basically when we talk about those stationary manipulators and all those things, so in those terminologies, inverse kinematic is a process that given the position and orientation of the end effector, we need to find the joint angles. Suppose it's a 3R manipulator, a stationary manipulator. So the end effector we have given the coordinates and position and orientation of the end effector, that is x, y, z, and the Euler angle, that is roll, pitch, and yaw. So we need to find the joint angle. That is in 3R manipulator we have three joint angles for three arms. That is theta 1, theta 2, and theta 3. So using inverse kinematic algorithm and the complicated geometries, we somehow find the angles that given the position x, y, z, and roll, pitch, yaw, we find theta 1, theta 2, theta 3. So it's the inverse kinematic algorithm in case of stationary fixed base manipulators. So for path planning also we follow some process. Given the position of the goal node or the goal point, we calculate the current position of the robot, and using the kinematics and dynamics of robots, we calculate the torque that is being required to give to the suppose it's a four wheel differential drive robot. So we calculate the torque required to give to the right wheel, and similarly we calculate the torque that is required to drive the left and right wheel both. So this is a path planning algorithm, and accordingly it generates a suitable path, means on application of RRT algorithm, which is the second step. So then we apply this RRT algorithm. Of course, means if RRT applies, then it's a collision avoidance algorithm. So first we apply that in 2D space, and then we apply the same algorithm in 3D space. So there's only this inverse kinematic part to deal with the z coordinate. So we require so this conversion from 2D to 3D doesn't actually create a problem because the z coordinate is almost zero only. So only we require z coordinates for this path planning algorithm. And similarly, we do it in Python 3.5.2. That is path planning. First, we do path planning, and then of course we have to do obstacle detection for collision avoidance. First, we need to do obstacle detection. Then we apply this RRT algorithm for collision avoidance in 2D space, and we have done it for user-defined obstacles. Like we already know beforehand where are the obstacle and all those things. It's not autonomous. We have to define the predefined map of the environment, or we can use SLAM and other techniques for real-time obstacle detection. And then we implement this model in 3D space, and then we have validated our results in our smart factor lab with the original. So the methodology we use for this RRT algorithm is that RRT is a basically a sampling-based planning algorithm. So the points of the in this method, the points in the environment are represented as nodes. So we have here input node as you can. This is the algorithm. This picture might not be clear, so let me explain it. So the inputs are the locus of the start point, the locus of the goal point means the positional coordinates of the start point, the goal point, and since if we see that it can be an infinite loop, so we need to define the number of search nodes. Means at every point, means first we have to define the number of search nodes. That for this experiment we have taken the number of search nodes to be 1,000. So means at every point the algorithm runs thousand number of points around that particular point to search for the optimal point. So I will explain that how this optimal point is calculated, and then again we have defined a error threshold, which for this experiment we have taken it as 5 mm. So error threshold is nothing but the distance. Means we create a threshold that 5 mm radius. Suppose that if the robot reaches near 5 mm radius of the target destination, then we have to stop this algorithm. So the output of this algorithm is P, that is locus of points, means the current point. So we assign P dot current node is equals to start. Then while P dot current node is not equal to goal, or or the distance between current node and goal is greater than the error threshold, when the robot first of all the robot current position is not the goal position, when the robot is not at the final point. Hello, am I audible? Yeah. So robot is hello.
Yes, yes.
Yeah.
Yes, you are audible.
Yeah. So robot is not in its goal location, and the second condition is that the distance between the current node, means where the robot is, and the goal node should be greater than the error threshold. Then it enters a for loop, uh, which starts from 0 to the number of search nodes that we have defined, like 1,000. So it starts so that it enters in the loop, and then for every 1,000 iteration, it calculates points. It calculates random point around that particular point, and for every iteration, it calculates the minimum distance between that particular random node and the goal. And then how it selects the optimal point is that it calculates the minimum distance between that random node and the goal node. So we have approximately, so we created an array of 1,000 points, So the distance between each point to the goal point uh, is again stored, and what is the minimum distance we return, and the point corresponding to the minimum distance we return that point as P again back. So that particular P point, that is locus of the current node. So now, so this process continues until one of the leaf node reaches the goal node. And when it reaches the goal node, means either of the condition is satisfied, either this P point is the goal node, or the distance between the P point and the goal is less than the error threshold, then our algorithm stops and the robot reaches its goal position. So this is the problem formulation that we have done. So for this experiment, we have created a 2D Cartesian virtual workspace of width 400 mm, and the height is 500 mm. So uh, we have defined start node, goal node, and obstacles. We have different types of obstacles also. I will come to that later. And we have created all this environment in Pygame software because it has very good attractive multimedia features and all those things. So we have used Pygame for this. And to reduce the complexity of code, we have assigned mouse clicks as trigger events. And as I've already told that, okay, so there was a mistake that I have told it was 1,000 iterations. So in this, we have number of iterations or number of search nodes, we have assigned it as 2,000, not 1,000. Sorry for that. And error threshold is 5 mm. And so we have various types of obstacles, like we have continuous obstacles, we have distributed obstacles, we have obstacles of high density, we have obstacles of low density, we have obstacles encapsulating the start, and we have obstacles encapsulating the goal node, and so on. We have many others, but these all categories are for particular for an industrial environment. It's according to previous literature and research. These are the basic types of obstacles that we would categorize in an environmental setup. So for this experiment, we have, following the color codes of the workspace, we have dynamic obstacles are represented by black color, and start means the start point of the robot is represented as red color. I will show it in few, means there are many graphs regarding this, so you will get to know that. And the goal is again represented by green color, and the exploration tree means the path that it uses, the RIT algorithm uses as represented in blue color. And the optimal path that is being generated by the RRT algorithm is again of green color. So this is color code for a RRT algorithm implementation. So following are the parameters that we use for this means that we use to to categorize our results. So the types of so basically there are different types of obstacles that I've told you, like concave obstacles, encapsulating. So here we could see that we have 6 types of obstacles. So I will go on one by one. So we have concave obstacles encapsulating the start goal, the start point. We have concave obstacles encapsulating the goal. Then we have obstacle density as both discrete uh, and low. We have obstacle density as discrete and high. We have obstacle density as continuous and low. Then we have obstacle density as continuous and high. And out of these 6, for each we have two. That means for each, suppose for this concave obstacles encapsulating the start goal, we have two conditions that when the start goal and when the start point and the goal point are nearer, means the distance between the start point and the goal point is less than 100 mm. And similarly, we say that the start point and the goal point are far when the actual distance between the start and goal is greater than 100 mm. So in total, we have 6 of these main categories, and under each category we have near and far category. So in total, we have 12 such categorization of the obstacles that is usually found in our industry. And we have the actual distance between the start and the end, um, and then we have number of points generated as path solution. Okay, and then we have path distance, means the distance of the path that's been generated by the RIT algorithm. And finally, the difference between the path generated by the algorithm and the that's been and the actual path is the path difference. So with these 5 criteria, along with this 12 obstacle arrangements, so now we can proceed to our simulation part. So this is the smart factor setup where we have performed our result experimentally. This is the smart factor setup in CPDM at IISc. So here are the results. So I will just no, I will provide a detailed description of only these two cases, like concave obstacles encapsulating the start, and yeah. So rest all the results I will explain, but not in detailed explanation. So as you can see that here, the red one, as I have told you in the color code, that red one is the start point, and green one is the and the green circle is the goal point. And as you can see that this, I think so, it might not be clear, but this green path, as you can see from here, is the path that's been generated by the RIT algorithm. And all these blue paths are the paths that's been traced by the RIT algorithm. As you can see, the start point has the coordinate 200 for this value. So as you can see from the figure, the start and goal node are nearer to each other. Means the distance between them. So so the start uh, so the start point has coordinate as 218, 250, and the goal point has a coordinate as 221, 200. So we calculate the distance between the 2 points using distance formula. Simple. So if we find that it's less than 100 mm. So we categorize that when start and goal are near to each other. And we have this concave obstacle, that is black one, that's encapsulating the start point, which is red in color. So the actual distance between the start and end is is calculated to be 50.09 mm, and the number of points generated as a path solution is 59. And if we apply the RIT algorithm, then the distance between these two paths, means the distance that's been traveled by this robot, is just 50.93 mm. So the path difference is the actual difference uh, minus the difference between the path that's being generated by the RIT algorithm, or taking the mod. So the distance of 650.93 minus 50.09, it comes out to be 600.84. So that's the path difference. As you can see that this path difference is very high. I will explain that in the conclusion section, where I will say that why this path difference is that much high, 600 mm. So 600 mm, it might not seem that it's it seems to be very small, but when you apply it actually in an industry environment, it could result in serious injuries and all those things. It could be fatal, because 600 mm is very large value when we consider it from an industrial perspective. And then we have again the same situation, but the only thing is that here the start point and the goal point are far away from each other. you can see the start point has coordinates 45, 444, and the goal point has coordinates 432, 172. So if we calculate the distance, it comes out to be 4. Means the actual distance comes out to be uh, uh, 473.02 mm, and number of points generated as a path solution is 55. And then we calculate the distance that's been traced by this RRT algorithm as the distance along this green path comes out to be 604.24 mm. So if we subtract this 604.24 minus 473.02, it comes out to be 131.21 mm. The part difference, which is quite it's acceptable in industrial environment. It means it's very less as compared to the 600 mm. So these two are the condition. The first one is when the start and goal are nearer, and the second one is when the start and goal are far from each other. So, uh, yeah, sorry. So, yeah. So here's the RRT path under different obstacle densities and distributions. So this figure might look dirty because of this all this blue path that's being tested by the RRT. So the first one is that I've already explained. The start and goal are nearer to each other, and the start point is concavely surrounded by an obstacle. So here we could see this. This condition that's generated by the RRT algorithm. So basically, this result shows that different obstacle shows the RRT path generated by the algorithm under different obstacle conditions and variations. So this is similar. So this is similar to this one only, but means that in a sense that goal and the start point are near to each other. The only thing that instead here the start point is surrounded by the obstacle, but here the goal is surrounded by the obstacle. So again, we have some result here. I will explain the results in the later slide. For now, just see the various distribution of obstacle that we have simulated in, and here we have continuous. So here we have continuous obstacle, and the start and goal points are far from each other. Okay, and means the distance between them is greater than 100 mm, and the obstacles are continuous obstacles, and they're sparsely distributed. Means they have low density. So again, we have this green path over here, and it is a continuous obstacle, but of high density. Means they are very clustered, and the goal point and the start point are nearer to each other. Similarly, the start point and goal point are far from each other, and the goal point is surrounded by the obstacle. Similarly, we have here the objects used means the obstacles used as discrete distribution, and they are densely distributed. So we have discrete and of high density. And apart from this, the goal and the start point are far from each other. So again, we could see that the RRT algorithm is from here, here, here. So we have the RIT algorithm. We can see that it's mostly, it just travels from outside of the boundary and then it reaches the goal. That's why the path difference also is high for that case. I will show you in result section. And again, here we have, different discrete distribution of the obstacles and of sparse density or low density. And the goal and start node are far from each other. So from here, again, we have this green path. That's the path generated by the RT algorithm. Similarly, we have continuous obstacle, but the difference is here the goal and the start point are nearer to each other. And we have this, again, we have discrete distribution of the obstacles, means they are point obstacles. The discrete distribution means we have small point obstacles like a manipulator or simple, or simple spots that we are not allowed to go or something like that. And this continuous obstacle can represent human beings or something, or like a big table or where the robot is not allowed to go. So this is a discrete distribution, but the density is very high. Means they are very clustered, and the goal and the start point are nearer to each other. So these two cases, this case and this case are similar, but the only thing is that here goal is far from each other. A goal and the start node are far, and here goal and start node are nearer to each other. And this is a distribution where we have discrete distribution of obstacles, but they're densely distributed. Means they're crowded. They have high density. But the thing is, goal and start node are nearer to each other. So basically, this graph and this graph are similar, but here the goal and the start are nearer to each other, and here the goal and the start point are far from each other. So we all, so in total we have two distributions I've told before, and we have total here 10 distributions. So we have 12 such distributions, and we have simulated our RRT algorithm in these obstacle distributions, and then we go on to result section, that is this section. So yeah, so we could see from here is that this is the part difference versus type of configuration. So as you can see, the y-axis represents path difference in mm. So yeah, and the x-axis represent type of obstacle configuration. So for we have six different categories. So the and for each category we have the yellow one represents near zone. Means this graph might not be clear. I will give you all the data. So the yellow one represents near zone, and the blue one represents far zone. And we have such near and far zone for all the six obstacle distributions. So we in total we have 12 such graphs. So the first graph is for concave obstacles encapsulating the start goal. So here we could see, as from the diagram that I have shown you in the detailed description, you could see that the path difference is 600.8 per mm, which is very high. So we could see that it's around 600.84 mm over here. So the reason is that when the obstacle encapsulates the start point, the and when it's nearer to and when the goal is near to the start point, what happens is that the robot spends not actually the robot, the RRT algorithm spends most of the time circling around the obstacle only. Means just after it start a few of those iterations after it started, it just circles around the obstacle until and unless it sees a correct state. Then when it it just encirculates when it just traverse almost half of the distance of the obstacle, then it goes straight toward the goal point. So while traversing the obstacle, it creates such a high path difference. So yeah, because so that's why it's not beneficial to apply RRT algorithm in such situations. And for fast zone, what happens? The path difference is less because because the obstacle encapsulates the goal node. So what happens when the RRT algorithm starts from the start node? It just goes straight to the goal node, and when it reaches the goal node, there it finds an obstacle. So what happened? It just move a little bit around the obstacle, and then it just reaches inside the error threshold, and the algorithm stops. And so we could say that the robot has reached the goal. So in that case, the path difference is under limits. That is 131.21. So similarly, the path difference are when we consider. So the second one is that category of obstacle, that concave obstacles which encapsulates the goal point. So in that case, we see that the path difference are almost comparable in case of in case of encapsulation of goals of goal load. The third one is for discretely distributed obstacle with low density. With low density. So what happens here? The obstacle is discretely distributed, and moreover, apart from having discrete distribution, the obstacles are sparsely distributed in the whole workspace. So what happens when the robot is at its start point? It after just few iterations only it directly reaches to the that are target destination. Uh, in between, it might encounter some obstacles, but that's not much because again, due to this configuration that it is sparsely distributed when the density is low. So in this case, we see that the RRT algorithm is very effective and it gives very less path difference, that is approximately around 35.99, 35.59 mm. So it's acceptable under normal conditions. And when the object is in far zone, then sorry, not the object, and that means when the distance between goal and the start node is greater than 100 mm. So again, in this case, we see that the part difference is approximately 270.15 mm. So this is the case for discretely distributed obstacle, but for high obstacle density. So we see that these two follows similar trends for near zone and similar trends for far zone also. So this is because for near zone, exploration occurs in almost a free workspace. And for far zone, most of the workspace is explored by RRT. So therefore, higher variation might be there, and hence we have higher part difference for far zone. But the advantage of high obstacle density is that the search space is minimized. See, if the obstacle density is high, See, most of the time what happens, the robot tries to figure out this path, outside the, that cluster of obstacles. But by chance, suppose if the robot finds its way through the high obstacle density, so what happens, it doesn't, the obstacles doesn't allow much variation. Means whenever the RIT algorithm is implemented, whenever it finds an obstacle, it terminates. So that's why there's not much variation, and hence for high density, the search time is minimized, leading to faster convergence and less variation in results. So for high density also, this RRT algorithm is very effective. And similarly, for this fifth distribution is of continuously distributed obstacle with low obstacle density. So as you could see that these two are follow similar trend in the first and the last one and the fifth one. And this one is for continuously distributed obstacle but it's of high obstacle density. So it follows similar trend with respect with as we compare from the concave encapsulation of a start and of a start point and goal point. So the results are similar because path traced along the obstacles are straight and in almost in free areas, and in the far zone, contouring along large obstacles increases the path difference, means very badly. Means as I've told you in the earlier part also, that when the obstacle encapsulates the goal point, or sorry, the start point, the RIT algorithm spends much of the time traversing along the obstacle only. So that's why the path difference is very high. So these are the results so these are the conclusions basically that we have derived. So coming out of this, so we have seen that when dynamic obstacles surround the start point, path difference is higher in near zone than in far zone, and RRT has a lesser extent of contouring around the means it has a lesser extent of contouring around sparse obstacles like obstacles of low density than continuous obstacles. Therefore, the path along this continuous obstacle increases. Means it's much higher as compared to a sparse distribution. And we have implemented this RIT algorithm in our smart factory environment using a real-time depth sensor, that is Intel's real sense camera, and simulations and experiments carried out to implement RIT algorithm in certain temporal human activity based on obstacles in Industry 4.0 setup. So we have validated our results experimentally also. So like this, we conclude that RIT algorithm proves to be a much efficient and more better way than other algorithms when it comes to navigation through complex cluttered environments in mostly like in a industrial setup. So here are some of the references. And yeah, that's it. So if any questions, I think so you can ask questions now.
Thank you, Mukund.
Yeah.
Yes, if anybody has any questions, please you can unmute or you can raise your hand. Yeah, I can see one raised hand. You can unmute yourself and ask.
Hello. Mukund, I have doubt in the algorithm part. So can you go
Yeah.
to the algorithm slide?
Okay. Yeah. Sure. Yeah.
Yeah. Like here, you will choose a random node from
Yeah.
the current node, and then you're doing if min of distance between the random node and the goal. So
Cool.
I didn't
Yeah.
understand what is happening there. Like you're just
Okay.
doing the min of one distance, or like are there any
No,
other?
no. Wait, let me explain you. So, suppose a robot, can you see my pen over here?
Yeah, yeah.
So suppose this is the point that a robot currently is in. So I think so here we have taken, hello, am I audible?
Yes, yes, you are audible.
Yeah. So here we have taken in an experiment 2000 nodes. So first of all, in this loop, it will search that if the if this current point is not the goal point, or suppose if this current point is not the goal point, and the distance between this current point and the goal point is greater than 5 means the error threshold, then the loop will start. This for loop will start. So we have taken 1000, sorry 2000. So here around it will search randomly search for suppose 2000 points around this particular point, like this, like this, like this. You know, every point means every angle it will search around 2000 points. And then what happens? It calculates the minimum distance between this random node. Suppose this is the goal point. Okay, this is the goal point. Then what happened? It calculates the distance of every point with this goal point. So suppose it is d1, and suppose again this is d2. Okay, so like this we have total d2000. So then it stores an array over here that is of the minimum distance. That is, it is from d1, d2, all the way up to d2000. So what happens? So the as you can see, as you can logically infer that the next, so it has to go from this point to the next position, which is among these 2000 points. So what is the minimum? So what is the criteria that the distance between? So optimal path will be when the distance between this point means the next point and the goal point is minimum. So this if minimum distance between the random node and the goal is minimum. So suppose from here we find that d3 is the minimum. Okay, this distance comes out to be minimum. So our robot moves to this d3 point. So if so now d3 point is p, means the coordinates of the d3 point is p. Then it returns the value of p again. So again, so now the robot moves from this point to this p point. Then again it searches for 2000 iterations around this p point, and then it again calculates the distance of each point from the goal point, and then it again calculates the minimum distance. And what is the minimum distance? It again moves to that point, means the index location. So like this it works.
Yeah, got it. Mukund, is there any heuristic for choosing the number of search nodes? Like
No,
how
that's a
are you
drawback.
able to
No,
2000?
that's the drawback of this algorithm that I've told you. You can see that from this figure, it just randomly chooses. That's why the name it's that random. The random name came from that only. It chooses randomly. There's no heuristics in that. Heuristics we have in this A star algorithm, and even in this RRT star algorithm, this RRT star algorithm, we have not actually we have heuristics, but we have defined a radius that suppose this is the start point, and we define a suppose this radius. So it just search those 200 points in this radius only. So we have that in RRT algorithm, and heuristics we have in this A star and modify A star algorithm, where we select these nodes and it goes from this node to this node, and finally like this and then we assign a cost from going to one node to another node, and then through backpropagation it calculates the minimum cost, then it finds the most optimal path. So we don't have any heuristics in RRT algorithm. Yeah.
And then when the obstacles are densely populated,
Yeah.
have you taken care of the size of obstacles and the size of robot and the relative distance between the
Yeah.
obstacles?
Yeah. So when the obstacle reaches, so what happens? Yeah, when the obstacle reaches, the algorithm stops over here. Means it doesn't go forward
I
with this.
mean, not when it reaches the obstacle. I mean, I'm saying
Okay.
when the obstacles are densely populated. So there will be gap between the obstacle, right? But this algorithm will say that there is a path because of
No,
that
no,
gap. But robot
no.
might not be able to move uh, with that gap. So have you taken care of will this algorithm
Yeah.
allow us to take care of such things?
Yeah, means suppose there's a very small gap between these two obstacles. So if the robot, so if the RRT algorithm, suppose, means I got your point. You're telling that if the RRT algorithm finds a path through this, but the thing is that the robot dimensions is much greater than the path between these two.
Yes,
No?
yes, correct.
So in that case, this RRT algorithm fails. Means it should be not that much. So we need to assign. So that's why I told that we haven't given that those things to this robot, that the size of the size of the robot, and the difference between the obstacles, we haven't used any such formulations in our this environment. So that we use in this A star algorithm. So we are working on this A star A star algorithm. So in that we have such heuristics.
Okay, there was one more slide, like you showed starting point enclosed with concave obstacle. Yeah, like here, like why are you guys using path difference as a metric? Even if there are some humans start from this point and then reach the goal, so they have to go around the obstacle, right? Like why are you using straight line distance as a measure?
No, so because the state line difference is that suppose means the state line difference is only used when there's no obstacle in between. So suppose this is the state line over here, and the RRT algorithm search points from all over to here to here. So we have other criteria also to classify that what is the optimal path. Means there should be at least some criteria. No, means the path difference is nothing. Means it's not like that we are using only this method only. Suppose we are using just it as a reference scale to compare between various you know observations that we got. So I know that if there will be some human also, he couldn't just go all along through the obstacle and reach the goal point. The only thing is that to compare it in simulation wise, we we see that how long actually it means how far or how larger distance it travels along this RLT path as compared to a straight line path. Means we keep a straight line path only as a reference. We never say that that if there is a human, then he will directly move straight along. We just give this straight line path as a reference to compare our RLT path generated.
Okay.
It's just as a reference.
Thank you.
Yeah. Any questions?
I am seeing one in chat.
Wait.
Let me
Go to the chat.
read it out.
I don't think so. There's question. Yeah, you can read it. Or wait, let me read it out. So the minimization, taking the shortest point among the 2000 points is localized. It is not the best minimized point to reach the destination. Wait, let me understand. So the minimization is localized, taking shortest point among the 2000 points. So it is not the best minimized path to reach the destination. Yeah. So actually, this is not the best part, but for the sake that we are using, since we are using this in a random fashion, so obviously it will not be the optimal path. Means we need to have some heuristics or some predefined method to actually find the optimal path. So even when we talk about optimization, we actually don't get the optimal path. We are near to the optimal path. So for the same case also, among those 200 points, I mean, we don't say it's the optimal path, but among those 200 points and among the calculations, that's the best path that we could choose among those 200 points. Yeah, it's not the optimal path, but it's the best path among the 200 points. We can never reach optimal path. I hope so it's clear.
And one more raised hand is there. Nishchal, you can unmute and ask.
Yeah. So the numbers that you've given here in this specific slide 10. So are these average numbers or for a particular simulation? Because we are
Average number
exploring
means
randomly, right?
yeah. Average number means what number are we exactly talking about?
The 650.93 distance between the distance of the path generated. Since we're exploring randomly, it might be different for different simulations.
Yeah, it might be different for different simulations, but for this particular simulation, the length of this path is 650.93. Means the robot that is being traced over here, it's 650. The path.
Okay.
Yeah, it's not the average, but it's the.
Do you have any results on? Yeah, okay. Do you have any results on average? I mean, that might give a better picture, right?
How can average give a better picture? Means I couldn't get. Can you?
So we probably we can do more number of simulations, and average out the distance of the path generated.
No, yeah, we could do that, but we don't have. But we didn't do this. We just directly tested it in a real time situation. So we don't. means we don't have taken many data of particular case. Yeah.
Okay. Okay. No problem.
Just taken one case.
Thank you.
Any questions?
There are no more raised hand now. So maybe we can move on. So thank you, Mukund. As a token of appreciation, I would like we on behalf of Vice community would like to hand over plaque. Like this is not a, a physical meeting, so we are not able to give any memento. But yeah, I request Swati to. Yeah, this is the one.
Thank you. Thank you, Parth.
Yeah, thank you. So I'd like to request Swati to deliver a vote of thanks.
Thank you, Mr. Mukund, for delivering such a wonderful and insightful talk. With that, we come to the end of this webinar. It was our pleasure to host you all for this human-aware robot motion planning using RRT algorithm in Industry 4.0 environment. I hope you enjoyed the session and that you found it useful as a future work direction or for your present work. I'm also thankful to the IEEE Bangalore section and to the IEEE Bangalore section and IEEE IISc Vice branch for the support in organizing this event. On behalf of the organizing committee and the attendees, I would like to thank the speaker again. And my thanks goes to the student committee members who helped in the successful hosting of the webinar, Ms. Prachi Singh and Ms. Swati for coordinating and hosting the event, Mr. Varki John, Ms. Ananta Kant Rai, and Mr. Kundan Kumar for the technical handling. I would also like to thank Professor T. Srinivas and Professor Anandi Giridharan for guiding the student team members and all the committee members for reaching out and making this event successful. Thank you all and have a good day.
Yeah. Thank you, everyone.
Thank you, everyone.